right, so I want to start now with giving an overview of how we'll prove the classification of surfaces. And it'll take us a few lectures to work out some of the details. So last time we stated this classification of surfaces, which says that every closed surface is obtained from the two-sphere by annulus and Mobius attachments. Okay, so we describe these two operations on any surface, and the classification of surfaces says you can get to any surface by starting with the two-sphere and doing some combination of these operations finitely many times. So the proof outline is as follows. So there's 3 steps. The first, which will be the focus of part of today's lecture, is that surfaces can be triangulated. So this is an important step because it allows us to do things combinatorially. The second step is to consider an operation which is called surgery. So surgery, this is an inverse to annulus or Mobius attachments. And well, the picture is like this. So you start with some surface, and you find some loop in the surface, which doesn't bound a disk, and then you cut the surface along that curve to get a surface with boundary now. So now there's going to be 2 boundary components, and then you fill these with disks. And the effect of this is removing the number of holes in the surface. So this operation produces a simpler surface, and we'll make, well, yeah, so here simpler means it has fewer holes. Or another way to say this, which is a little more precise, is that this surgery operation increases the Euler characteristic. So we'll discuss that a little later. And then, well, the third ingredient in the proof is to show that, well, for any triangulated surface, so S is the geometric realization of some triangulation, the Euler characteristic of K, so this is vertices minus edges plus faces, is at most 2. And with equality, if and only if the geometric realization of K, which is topologically equivalent to the two-sphere. Okay, so I guess here I should say that the Euler characteristic increases. This is what it means to be simpler. And right, so the Euler characteristic increases, but the Euler characteristic is bounded from above by 2. So at some point, you have to get to the sphere. So, okay, so combining all 3 of these steps, one concludes that after finitely many, so given our surface S, after finitely many surgeries, we get the two-sphere with a finite set of disks. I'm going to say marked disks. So you get these special disks, which are the disks you fill in here in the surgery process. And then, well, to conclude, so reversing the surgery describes S as obtained from annulus and Mobius attachments, which is what we wanted to show. Okay, so this is the proof outline, not the proof. There are many details missing, but this is the idea. So we have this surgery process that reduces the complexity of a surface, increases the Euler characteristic. If we apply this finitely many times, we're going to show that, well, yeah, so doing this operation increases the Euler characteristic. Eventually, you'll get to the two-sphere, and then if you retrace your steps, you see that since the surgery is the inverse of annulus or Mobius attachment, going backwards from the surgery, once you get to the two-sphere, going backwards then describes your surface in this way, as obtained from annulus and Mobius attachments. Okay, so that's the idea. All right, so now I want to start with the first bit here, that surfaces can be triangulated. Right, so the theorem, which I want to discuss, we won't prove it in full generality, is that any surface has a triangulation. Right, so first let me try to convince you that there's some serious work that needs to be done here. So I guess on homework 8, you gave triangulations to some surfaces, like the torus and the Klein bottle, or the annulus, maybe. And, well, right. And I guess by the classification of surfaces, we know sort of what all the surfaces are, and we know we can triangulate each of them. But that's circular reasoning, because we want to use this triangulation to prove the classification of surfaces. So you're supposed to think that we don't really know what all the surfaces are at this point. And we're given some mystery surface S, and somehow we have to come up with a triangulation. And this is a seemingly hard problem because, well, I mean, you're just, well, what do you do? I mean, this surface, you just know that it locally looks like the plane, and somehow you have to produce a triangulation. So, right, so here's well, I'll call this a proof sketch in a special case. So this won't prove the general theorem, and I won't give you all the details, but this is a good first step. So the special case is that we're going to assume that S is a subset of R3, and that it's smooth in the sense of calculus, which is to say, so near each point P in S, S locally looks like a plane, a linear subspace R2 and R3. Okay, so we know locally S is topologically equivalent to R2, but this extra smoothness assumption is that really locally, if we zoom in close enough, then S looks actually like a linear subspace of R3. And this is like one of the basic ideas of multivariable calculus. So you have some surface and some in Euclidean space, say three dimensions. If you zoom in, well, okay, if it's smooth, then there's something called a tangent plane, which is like the plane of best approximation at this point P. And if you zoom in close enough, then the surface looks like this plane. Okay, so this is similar to in calculus, the graph of a function, if you zoom in close enough, just looks like a line. And that line has slope the derivative. And of course, this is assuming your function is differentiable. Okay, let me not say anything more about that for now. Right, so given, well, yeah, so another way to say this is we can, well, okay, given P, we can choose epsilon positive and very small so that if C epsilon P is the cube of side length epsilon around P, centered at P, then S intersect this cube is roughly like a planar cross section. So let me draw some pictures to illustrate what I mean. So here's cube centered. You're supposed to think of P as in the center of this. And I'm just going to draw some possible pictures for what a planar cross section might look like. let me just make several of these. So, okay, I mean, so you take a plane in R3 and then you have this cube and you see how that plane might slice through the cube. I mean, it might look something like this. Some horizontal slice, maybe it's vertical or in a different plane. You might have something that sort of crashes through diagonally like this. The slice doesn't have to be a square. If you slice off a corner, and you might see some triangle here. Are there other ones I wanted to draw? I think there's a cross section which is a hexagon. I think there's a plane whose cross section, I guess this picture looks maybe convincing. You can have a hexagonal cross section. And maybe there's some others, but well, there's really only finitely many combinatorial types that you can get in this way. But right, so the statement is if we fix our epsilon small enough, then the surface looks inside of this cube looks like a plane. And so then the picture of the surface in this cube is just some planar cross section. Right, so let's see, where are we in terms of the, yeah, so let me just write here. Oops. So here are, okay, sorry, make space. So sample cross sections. Right, so now what we can do is we can choose, so since S is compact, we can choose epsilon that, let me say, just works for all P. And by works, I mean so that if we have any point on our surface, P and S, then if we take the cube of side length epsilon centered at P, then the picture looks basically like one of these cross sections or a planar cross section. So then let's tile R3 by cubes of side length epsilon. And this divides S into polygons. So inside of every cube, if there's a piece of S in that cube, then it looks like some finite number of pictures, maybe one of these here. And well, that gives some polygonal description of S. We're aiming for a triangulation, but this is a good start. So you have vertices for along the edges for how S meets this thing, and then there's edges and faces. And then we can further divide each polygon into triangles. So, I mean, if we're given a hexagon like this, then, well, you can just do something simple like this. All right. So as an example, okay, so this is the sketch of the argument. Choose a small scale, small enough so that any cube intersect with the surface is going to look polygonal. Then you tile all of R3 by cubes centered at some lattice points. And and then that gives you a polygonal decomposition of the surface, and then you further decompose it into triangles, and there's your triangulation. So as an example, if we take the standard two-sphere in R3, and we use cubes of, well, let's say we use unit cubes. So, well, okay. So like here's, and let's take them, like here's a unit cube here. The sphere sits in this picture, something like this. Here's just one octant of the sphere. And then up to, well, yeah, up to replacing this by a plane, then we get a description. So if we replace this round triangle just by a flat triangle, and we do that in each octant, that gives a triangulation of the two-sphere as an octahedron. So let me draw it like this. We have the points with positive z coordinate, and then points with negative z coordinate like this. So this is, you get this decomposition of the two-sphere into 8 triangles. This is the octahedron. Okay. So some remarks about this argument. So the first is that, well, not every surface can be embedded in R3. So let me say embeds in R3. Sorry, let me write it this way. Embeds S, a subset of R3. So for example, the projective plane or the Klein bottle don't have a nice embedding in R3. This takes some work to prove, but for the Klein bottle, you can kind of see why this is difficult, because remember, the Klein bottle is obtained from a annulus attachment, where you take an annulus and you attach on one side, well, you attach the circles like this, and well, here at some, if you just try to draw this in 3 space, you're going to crash through the sphere. So you don't get an injective map of the Klein bottle into R3. Right. Okay, so okay, this is just a remark. But every surface does embed. They do embed in R4. This is a difficult fact. So this is kind of a fact of differential topology, and these embedding questions, well, an important theorem is something called the Whitney embedding theorem. So I'm not going to go down this road, but this is a topic of differential topology. So you can learn about it there. The other, and yeah, so I mean, this argument, we didn't really use R3 in a crucial way. You could do a similar argument if you have your surface embedded in some higher dimensional Euclidean space. And then the other remark I want to make is that, well, there was this extra assumption here of smoothness. I mean, the surfaces we have, they don't have any smooth assumption on them. I mean, they're just topological spaces. So we're not doing calculus, we're just doing topology. But as it turns out, every surface, I'll just say, has a smooth structure. Well, okay. I don't really want to explain. This would take us too far afield. And this turns out to be a hard fact. So I won't attempt to say anything more about it here. Okay, so at the end of the day, the main takeaway is that surfaces have triangulations. And these triangulations have some special properties. So the triangulation that was constructed in this proof sketch, it has the following properties. So first of all, it's two-dimensional, which is to say there's no k simplices for k at least 3. There's just vertices, edges, and faces. It's every edge meets exactly 2 faces. So the edges of this triangulation, well, there's the edges coming in the interior of a polygon, but the other type of edges, and those are in 2 faces sort of by construction. The other type of edges are these edges that are along the face of a cube. And the simple fact is that 2 cubes, or each face of a cube is, each face is in exactly 2 cubes. And so this, any given edge, there's going to be another cube sort of adjacent to this one with some other, maybe some other piece here, and that's will be the other face that contains this green edge. So every edge in the triangulation is in exactly 2 faces. Okay, that's the second property. The third property is, well, every vertex, I'm going to say, has a pizza neighborhood. Which is to say, if you take a vertex and you just look at all of the triangles that are adjacent to this vertex, then it looks like, well, slices of a pizza, something like this. I mean, a priori in a triangulation, you could have lots of weirder things. I mean, you could just have a single triangle, or maybe you have, I don't know. I mean, maybe you have, I don't know, like this sort of picture, and there are triangles coming off of up and above and below in a weird fashion, but this third property is saying that that sort of weird stuff doesn't happen. You just have triangles that lay down in a nice way going around your single vertex in a cyclic fashion. And again, this just follows from thinking about how this construction works. At a vertex of the triangulation, you're either, well, here you're at an edge of the cube, and around that edge you see 4 other, right? You see 4 total cubes, and they fit together in a nice way. And so then you just think about how this construction works, and you see that you have this pizza neighborhood. Okay. So these properties, well, okay, so let me just say conversely, for a triangulation with these properties, the geometric realization, so this, the triangulation K with these properties, the geometric realization of K is a surface. These properties guarantee exactly that every point has a neighborhood which is topologically equivalent to the plane. And so, okay, so going forward, we're going to call a combinatorial surface this is a surface with a triangulation. And that triangulation is going to have these three properties. So I guess, yeah, one way to write it is S is geometric realization of some triangulation that will necessarily have these properties. Okay. Okay, so this is the first step in this proof outline. Surfaces can be triangulated. And that's extremely useful because then we have special notions for things that are for simplicial complexes. So the last thing I want to mention now is the Euler characteristic, which we've talked about before. I guess I called it the Euler number. So in general, for K, or let me say L, a simplicial complex, one defines its Euler characteristic as the alternating sum minus 1 to the n of the number of n simplices. So for n at least 0. So if K is a combinatorial surface, then the Euler characteristic of L, so there's no simplices there's no n simplices for n bigger than 2, and so we just have vertices minus edges plus faces. And if instead K was a graph, then it's just vertices minus edges. Okay. So the main thing I want to prove is the following lemma. I'll state it on a new slide. About the Euler characteristic of a combinatorial surface. So if K is a combinatorial surface, then the Euler characteristic is at most 2. And so as a remark, next time we'll show that the Euler characteristic is equal to 2 if and only if the geometric realization is topologically equivalent to the 2-sphere. But for now, let's just prove this statement. Right, so for the proof, let me remind you of a construction that we discussed at the beginning of the course. So first, what we're going to do is to choose a maximal tree T in K. So this is a tree that meets every vertex. And let's take G, the dual graph. So we defined this earlier in the course. So the vertices correspond to faces of K, and the edges correspond to edges of K not in T. So as a picture, suppose K is just the surface of a tetrahedron. We could take the maximal tree, something like, let's choose this back face in T. We just want to meet every vertex and not have any loops. I guess that works. So here's T. And we can think of G as sitting inside here. I guess there was a homework problem related to this. So there's 4 faces here. We connect 2 if they're connected by an edge that's not in T. So okay, so we've seen this. Right, so now the point is that the Euler characteristic of K, we're trying to show this is at most 2. So this is vertices of K minus edges of K plus faces of K. And well, the vertices of K is the same as the vertices of T, since every vertex of T meets every vertex of K. And then there are the edges of T, and also the edges of G, which are the edges of K that are not in T, so that's all the edges. And then there are the faces of K, which correspond to vertices of G. So here we see that the Euler characteristic of K is the sum of the Euler characteristic of T and the Euler characteristic of G. So now, I can't remember if we did this, what I'm about to say, so I'm going to mention it as an exercise. So if T is a tree, implies the Euler characteristic is 1. You can prove this easily by induction. And if G is any graph, then the Euler characteristic of G is at most 1. Well, this is not so hard to see because you could take a maximal tree, its Euler characteristic is 1, and then the difference between G and the maximal tree and G is a bunch of edges, and adding more edges just makes the Euler characteristic more negative. Okay. Okay, so then combining that, this means that the Euler characteristic of K, which is the sum of the Euler characteristic of a tree and some other graph, this is at most 2. And that's what we wanted to show. Okay. And right, so let me leave you now with one more exercise, which we'll use next time, which is that if L is a simplicial complex, which is a union of 2 subcomplexes, then the Euler characteristic of L is the sum of the Euler characteristic of L1 and the Euler characteristic of L2 minus the Euler characteristic of the intersection. The intersection, not the union. So this formula is fairly intuitive, and the intuition actually tells you how to prove it. Since L is the union of L1 and L2, any n simplex of L is counted either in L1 or L2, and if it's in both, then it's counted twice, and so you have to correct by subtracting simplices that are in both. Okay. So next time we'll talk a little bit more about the surgery operation on surfaces.